Hello, greetings everyone. Good morning, good afternoon, or good evening to all of you. Welcome to our webinar about classical and advanced control algorithms in different systems. Today, myself, Candan, and Parsa will be presenting you our webinar. Uh, Please note that you can share your questions through the YouTube's comment section. And by the end of the webinar, we will have a question and answer session, and we will try to answer all of your questions. Okay, so let's start with the presentation section, and then we will go uh, through the demo section as well. So, okay, today we will have five topics. We will go through five topics. First, we will introduce ourselves and also the Acrom as a company, and then we will go into the algorithms, like software part of it. Like we will introduce you briefly about classical and advanced control algorithms, and then we will go into the software and hardware implementation strategies of different control algorithms. We will have a live demonstration session, and finally we will have a short question and answer session. Okay, so let's introduce ourselves. I'll go first. My name is Candan. I am in the sales and marketing team in Acrom Robotics. Myself is an electrical and electronics engineer. And Parsa?
Hi everyone, I'm Parsa. I'm a mechatronics engineer and I work as one of the R&D engineers at Acrom.
Okay, perfect. So brief information about Acrom. First of all, like our name, it is like abbreviation of these three words, which is accessible robotics and mechatronics. And generally, this is what we do. Our company started like around 11, 12 years ago, and we are based in Istanbul, Turkey, but we are like operating worldwide, having like access to all the continents and working with our partners, with distributors, and what we are doing is like control and robotics education kits that are used in like higher education as well as research and typical similar projects. Now, as we are doing like robotic systems, and the control of the robots is like the what we are focusing on. Before going into the like control related topics, we need to first start with showing or explaining about what is a robotics platform, or what makes a product like a robotics platform. And for this, we are using an example unit, which is a steward platform. The image is just like a kind of a figure, but regardless of the product itself, every robotics or mechatronics platform has four things in common. The first thing is like a mechanical structure. So it is generally a moving part. Sometimes it is like a parallel plate, sometimes an end effector, or sometimes an object like a ball or a pendulum rod. This is the final goal of the robot. And second thing is the actuators. Actuators, generally there are electrical motors underneath actuators, but we have different type of actuators as well, linear actuators, like rotary. Sometimes there are like tensile rods, etc. Then there are kind of joint mechanisms connecting the actuators into the moving object, moving platform. The joint mechanism varies a lot as well. So like circular joints or linear joints, so on and so forth. And finally, there is the electronics part, where the algorithm is running, as well as all the power signals, all the electrical motors are fed, feedback signals are taken back. So this is like in general what makes a robotics platform briefly. Now, the heart of the robotics robotics platform is the software, because to achieve the final goal, to move an object from point A to point B, a software should run, and this software, when it is in the domain of the robotics, it is called the control software or control algorithms, in other words. And there are very different options for the control algorithms. So this part, I will ask Parsa to go through us from these two different, what they are meaning.
Sure. So in this video, we are going to talk about mainly two types of controllers, classic controllers and then advanced controllers, and the types that we use mostly in our devices. So under classical controllers, we would have on-off control, DP, PI, PD, and PID controllers, which is mostly used in the industry. And then we would have fuzzy logic control. Under the advanced controllers, however, we will need to talk about linear quadratic regulator, or the LQR control, the reinforcement learning, or RL, and ML-based control.
So let me go through the software implementation strategies or software implementation platforms or options we have. So I'm sorry, okay, that one. So for software implementation, there are three flavors, mostly asked or used platforms that we are also using, and also it is used all around the world. Probably. So the first flavor or first choice is a high level software. This is in general some graphical representation of abstraction of the system using MATLAB, Simulink, LabVIEW, Altair. These are like high-level software tools, generally used in the academic teaching space to teach the students the concepts of the platform, the concepts of the control algorithms. And next, the opposite counterpart is the low-level software. Here, the C, C++ programming language is used mainly. And that one has its own advantages, and generally the industrial applications, the real-world applications, or consumer applications, they all rely on this low-level software implementations. And finally, this one is more recent, but recent means at least 10 or plus years. The open source and kind of, again, high-level software tools. Here, the Python is the most dominant one. And also, with the booming of the AI and machine learning software and algorithms, there is always kind of an open source middleware in general, which is taking care of these difficult or more up-to-date implementation of the control platforms. So today we will be showing we will be showing examples or demonstrations for all these three software tools. For that, let's discuss a little bit about the hardware of where this software will run.
So choosing the right hardware is a key component. In this video, we're going to talk about three main hardware components that you can use in robotics. So first would be a Raspberry Pi, which is great for machine learning and for computer vision or data logging. Second would be a Arduino. which has a lower cost and limited sources, but ideal for PID, PD control. And then lastly, we would have the STM32, which has a 32-bit ARM core and has a higher performance rather than the Arduino.
And when we like match these hardware platforms with the software options, I think can you like tell me where we can run, or with Raspberry Pi what software we can run and so on?
So you can use Raspberry Pi and Arduino and STM32, all of them with MATLAB and Simulink. Also, you can write your Python codes for the Raspberry Pi as well, and just the Arduino codes for using the Arduino itself.
So in general, like low-level software is more like implemented on STM and Arduino, I believe. But when we go into high-level tools or open source AI, ML kind of tasks, more like Raspberry kind of single-board computers are preferred. Okay. So now, before going into the like demo sessions, the like example codes, for the people who doesn't know, maybe we need to give a brief information about the demo hardware, which is we selected today the ball balancing table. This one is first of all, it's a conceptual platform, a conceptual product. The aim of the product is very simple. So we try to move the ball on the top plate using two electrical motors. So because of these two electrical motors, we can tilt the platform in two dimensions. We call these dimensions X and Y dimensions. Hence, the platform is called 2 degree of freedom control platform. So the Parsa, can you tell us about inputs and outputs of the ball balancing table before going into the next section?
So the inputs would be the position of the ball, which is detected by the touchscreen sensor, which is on the table. And then the outputs would be a PWM signal sent to the servos.
I think these are the main components, and we have some optional add-ons that can give some further...
Like the IMU sensor, yes.
Yeah, exactly. So, and last but not least, the ball balancing table has all the software compatibility. We have the breadth examples in all different languages, which we will be showcasing today. So, that having said, so these are the available content that we generally provide, and some of them are like curriculum related examples. So curriculum topics are like introduction to modeling, system modeling, like controller design, and a little bit advanced controller designs as well. And on top of that, we have some like the advanced control example applications, which we will be showing today as well, one of them. So they are using like other tools a little bit out of the curriculum content. But let's go to next slide, and let us start with our first demo, which is maybe the simplest one. So I will briefly explain about the demo first, and then Parsa will take care of the software part. So the first demo, which is the classical controller PID, we will be implementing it on the Arduino microcontroller. And this system architecture also shows what we refer. So we have the servo motors, we have the touch sensor. The touch sensor input is measured, and the servo motors are driven with the PWM signal. So it is a very simple implementation. And in this demo, we will be showing it with the Arduino C IDE or Arduino IDE in the C language. but we also have the STM32 counterpart of the same example, as well as like MATLAB and Simulink. So now let's move into to the Parsas computer and let him show us the software.
Okay, so as you can see, we are on the Arduino IDE application, and we have our ball balancing table Arduino code ready. So first, we are going to define some variables like the touchscreen pins that are connected to the analog pins of the Arduino, and then the coordinates and filtering variables. Next, we will be defining the PID control variables like the PID gains, errors, and set points. Next, we will have to define the calibration offsets, but as you can see, these are all equal to 0 since there are no offsets right now. Next, we will have the actuators, the timing variables, derivatives, and errors for filtering. The second section of the code includes the setup. So it includes both servos and the PID tuning parameters. So these are predefined, but you can, of course, change them to see the results. On the next section of the code, we have the main loop, which the PID starts to work and show us how the table balances the ball at the desired position. So
we get the coordinates, we read the coordinates from a function, log, and calculate error.
And then the PID logic kicks in. You calculate the derivative and then filter the derivative to reduce the noise coming from the touchscreen, and then combining the PI and D variables. Next, we command the servos to move to the desired position. Here we see if there is no ball detected, just go to the center and all.
I think here is the loop timing. So in order to achieve the reliable microsecond or millisecond time intervals, and these are the functions, subroutines to measure the ball's position, right?
Yeah.
And error calculations, and this, I think this is how the code is looking like. Okay,
I think we can show the we can upload this to the Arduino and see how it controls the table.
Code. This one is a little bit dense content, but let me try to explain the concept first, and then Parsa will be showing us the code behind. So we will be showing you some LQR plus I, which is that becomes LQI control. This is like a optimal state feedback controller. So that is the Y extension through the LQR. So optimal or optimization is taking care of it. And maybe the question why LQI? So on the right hand side. So the main reason is to eliminate the steady state error. With the PID based applications, there is always a steady state error. It can be minimized, but it varies a lot with the changing conditions. If the ball's location changes, then the integral gain needs to be changed. Ball's mass, if the mass of the ball change for some reason, then again, every PID coefficient needs to be recalculated, retuned. There are adaptive PID applications as well, but the best thing in such kind of applications, like more optimal control kind of application, is supposed to be the LQI or LQR based control. So how it works, we will go also on the Simulink diagram. There are like four main sections of the code. The first one is like we will have state definitions and estimations, and there are the state space model, and then there is the calculation part, and finally we apply the control output and receive a feedback, and this feedback is fed to the observer, which is to make the optimal control for sure. So let's move and check the code. So Parcel, can you please
Sure.
explain us?
Let's display.
Simulink. Okay.
So let's display
Let's
the
display
Simulink.
Simulink.
So here is the main basic Simulink user interface, I can call it. So here you can give the X and Y reference points, and then on the right-hand side, you can see all the X, Y velocity and their velocity values inside some displays.
As well as the control signal, right?
Yes, exactly.
Yeah.
Yes. And then if we come to the background where the Simulink code is running, we can see three main parts: the LQI controller, the system, of course, and then the filter server. So starting from here, we will have to feed the loop our reference points.
Set points, right?
Or
In
set
other
points,
words.
yes.
Yep.
And then
have on
inside
left
the
we have the feedbacks, right?
feedbacks, and then inside the LQI controller, we can see that it gets the references and the measurements, and then as the output, it gives the X control and Y controls.
And on the left-hand side is like the state space representation of the states. Yeah.
And then next, we have the X control and Y control, of course, coming to the actuation system, and then you can see this here, which is fed into these gains, and then not multiplied, summed by the calibration values. We feed them to the servos through this S function.
So can you explain what this S function builder and where this is running? Yeah.
This S function is actually let me just open it. So it's actually written in C++, and then
this is just to drive the servo motors.
Yeah,
right?
yeah, just-
so of the
yeah.
and like maybe we would like passed quickly, but the algorithm is like it is running and being compiled, right, to the Arduino.
Yes.
Yeah.
Of course, we have this measurement part, which is separated from the actuation system. So we get the touchscreen coordinates or the coordinates of the ball, which go to the X measurement and Y measurement.
Again, it is an S
variables.
function.
Again, a S function that is read from the Arduino.
Mhm.
And then here in a loop, we have this filter observer for better.
Yeah,
better
for observer.
resolution.
So
Yeah.
for the optimal control. Yep. And can you open also the observer? So
Sure.
let's show the people what we have. So okay, so it's again a device builder block which is built with MATLAB Simulink functions directly, and every part can be like investigated or like changed really. Okay, so
I think this concludes
Okay.
this part.
So let's go to the third demo or third topic in our presentation. So what we have is this one will have some like demo session as well. The RL based or kind of like again an advanced control method. This one is actually like a combination of a classical controller, PID controller, which is still required to fine-tune the position of the ball, but the platform has a goal of moving the ball to solve a problem, and the problem is a maze problem. So we created a maze based on plastic parts, and the aim of the application is to move the ball to solve the maze and go to the exit of the maze. And that can be done with different methodologies for sure, but a reinforcement learning is a very good one to implement. Or ball balancing table is a very good example to implement the reinforcement learning application. So again, this one is it has like 3 or 4 steps or parts. The first part is kind of encoding the maze. So we tell the at least the starting and finishing points, and also we enter the wall coordinates as well. But it has to learn and do some path planning through this maze by hitting the walls and retreating back. And this is the path planning part, and where we are giving rewards or penalties based on the conditions, which Parsa will show in the code as well. And there should be some kind of small coordinate conversions to when teaching the algorithm. And the PID execution is just to move the ball like 1 centimeter forward, 1 centimeter backwards, or move to left or move to right to step in the execution or in the algorithm. So there can be future extensions of this work as well. But before that, let's first look to the code, how it is written, where it is written, and how it works.
Yeah.
So Parsa, please show
So
us.
the code is written in Python, and then if you see this, yes, as you mentioned, the first section is about configuring the maze. So
Before that, so it's running on Python, and which controller is it running on hardware side? Python, so
it should be Raspberry Pi. Yeah.
Mm-hmm.
So the first section, as you mentioned, is the maze configuration, using zeros and ones to represent the walls and the paths. And then you can also give the starting and finishing points here. On section 2, we have the RL setup. So here we have the QTable property, which is somehow
Which
the
direction is
memory,
up,
yeah,
which direction is down, and memory as well.
the main brain. And then we have the controls. On section 3, we have the helper logic, which contains the utility functions for coordinate indexing and movement validation. So as you mentioned, the up, down, left, and right
Steps, maybe,
Steps.
right? Small
Yeah.
steps or like jumps, maybe.
And then on section 4, we have we have the training of the agent, or Q learning. So this contains the core loop, where the agent explores the maze and learns from the rewards. So we have the reward and what's the
Penalties.
penalty? Yeah, reward and penalty system here.
So, for example, like what is the reward value?
So
there-
it should be 100.
yeah.
So it starts with 100, which is the goal, and then it subtracts 1 point for the shortest pass as penalties. And then for hitting the walls, it subtracts 10.
10 points. Yeah, right. And sector 5, I guess.
Yeah, so in sector 5, we have visualization of visualization utilities, which handles the plotting the results, showing the paths and agents confidence map. So would you like to talk about?
I mean, so here, like, it is like we show with different colors which path it's moved on a kind of a small heat map as well, and that like gives the idea about how it works. I mean, these are all kind of like cosmetics of the application.
Only the digital visualization.
Yeah. This is
And then the main entry point, which triggers the training process and displays the final solution. So I think we can show them a video,
Yep.
a demo video.
so,
So by the way, on the Acrom's blog webpage, you can see and read about this maze solver completely. So I will be showing you the demo video.
So the one thing that we don't do it on live like session, because it takes time to solve the
The video is
algorithm.
also 10 times faster than the usual. So.
But like it gives the main idea.
Yeah.
Right. So I think in this, like, starting point is selected on that left corner, and the goal is on the right top hand side. Something like that. Yeah. Okay. So let's go back to the presentation part and tell you about the future extension. So now we are thinking of like doing kind of a little AI implementation, maybe with deep reinforcement learning, and to solve like. Currently, it knows the starting and the goals, but in another iteration or implementation, it can do it blindly, and it can understand if it hits the wall, so the ball is not moving, so it can try to retreat back. So all of these are possible with some future work, future extensions. Now, let's talk briefly about kind of summary on the differences or advantages, pros or cons of using classical methodologies versus the advanced methodologies. So Parsa,
yeah, so
please.
starting with the PID or classical, we have the design part, which is actually the PID or gain constants, which can be tuned manually or using the Ziegler-Nichols method. And as hardwares, of course, we can use the STM32, the Arduino, and the Raspberry Pi as wished by the user. And then for the software, of course, you can use the Python, Arduino again, or C, C++ programming languages, as well as MATLAB and Simulink. So one thing that makes this more usable is that it is fast and easy to implement, or to be understandable and teachable. And what are the limitations are, so it does not adapt like the Q-learning, and for the ball balancing table, the real-time ball position regulation is used. So
for the when we compare it to the advanced methodologies, I think the main caveat or main difference will be the hardware selection. So it is really difficult for maybe not possible for low-end microcontrollers like Arduino or small STMs, the Q-learning algorithm or RL algorithms.
Yeah.
And also software part will be much more tricky than to do in C, C++. It is quite possible to do in MATLAB Simulink. Maybe we should have added it into our table.
Yeah.
But generally that is like kind of a trade-off. So one requires more resources, the other one achieves better results. So I think these were the main topics that we touched today, and from now on, where can the audience or listeners can go next? So our courseware, which includes these examples or main system modeling topics, they are all available online, so people can download it easily just going to our website. The codes, open source version codes, are all on our web page and also on the GitHub the repositories. For going deeper with advanced control, so there are many paths, many options. Time to time, some of our customers are sharing with us their papers or example videos, and we try to publish them on our website or on our YouTube channel as well. And finally, for people who want to try something but not able to access the hardware, so accessing remotely to the equipment is a possibility. We time to time discuss about this option with some people. So there are the resources over there, and before finishing the presentation part, I would like to discuss a little bit about Acrom's products, and for that let me go quickly to this slide. So ball balancing table is one of the products which today we selected as the demo system. But we have some other hardware in mechatronics and robotics, which are candidates of automatic control, or simple or complex or advanced control algorithms as well. We have upcoming webinars where we will be taking another product, doing some other demonstrations on that product and on different topics as well. So this concludes our presentation part, and now we will be going into the questions and if any answer session as well. Okay, so for people who would like to direct your questions, please feel free to write down in the chat box of the YouTube channel. Our administrator will be bringing it into our. Actually, I have one question, Parsa. Maybe you
Yeah,
can
sure.
help me a little understand that one. So, with in the there is a like a time scheduler in like Arduino, and I remember some customers were asking for they want to have tight time control, and they were claiming that the MATLAB Simulink, like when the code is implemented, it runs on a fixed time, but with a bigger like uncertainty or jittery. So is it better in the Arduino IDEs, or like is it a good choice to select like low level language over the high level languages?
Actually, yes. I think the Raspberry Pi using the Acrom's controller um, would be having a better control, but the Arduino is of course probably faster than Raspberry Pi because it doesn't have that kind of communication, I would say. So, by the way, the Arduino isn't that does not take that long.
Yeah. That's also
It
another.
is
Right.
controlled immediately, so
Okay.
it's not noticeable.
Relays.
Yeah.
Okay. So I think that we have a question. So here, this one. Let me read it, and Parsa
Sure.
will answer that. So it is from Carl Hurt, and he says that is there an AI interface option in writing or modifying the code for platform content or
Control.
Control, yeah,
Yeah.
you're right.
So the Acrom's codes, or let's say, codes and control platform does not have an AI yet to modify the control parameters, probably.
But I know you are using some Google's editor to like iteratively.
So so there are some applications that have how can I say it, built-in AIs that can help you, but those would be for Python.
Those for Python.
Yeah,
Okay.
Python only. No. So the MATLAB or Simulink models would not have an AI help for tuning control parameters.
But if it is for Python usages, that is something potentially doable. So, okay, we hope this explains, like, the answers the question, really. And if there isn't any further question, so let us wrap for today's webinar. And again, please watch or follow our website or email email announcements as well for the upcoming webinars. So this is actually the initial one, the first one, and we will have more webinars in the coming future. And then thank you.
Thank you all for listening and watching.
And
We will
hope to see
be
you soon.
seeing you soon. Goodbye.